Hi everyone, and welcome to your Math 100 orientation lecture. I am Dr. Ratilal, and I am going to be lecturing you for the rest of the semester. So this orientation lecture is made up of two parts. And so this video is part one, and then once you're done watching this, you should ensure that you watch part two. When watching these videos, I would strongly recommend that you also download the PDF notes that I have made available to you. Right, so what I'm going to do right now is I'm just going to briefly share my screen so that you can see the notes that I'm about to create. Okay, let's do that. Okay, perfect. So you now should be seeing my screen. I'm going to stop sharing my video for the time being, so I will disappear off your screens. All right, so this should be the PDF set of notes that you should be able to download so that you are able to see exactly what I am seeing or presenting to you during the video. Okay, so if you need to contact me and if you have anything urgent or any queries that you may have, then please drop me an email. My email address is cratilal@uj.ac.za. The prescribed textbook that you will require for the rest of the semester is Introductory Mathematical Analysis, the 14th edition. And this is for business, economics, and the life and social sciences. So I would recommend that you would perhaps, well, it would be good for you to get a physical copy of this book. And it would be good if you have it by the time we meet for our first lecture, which takes place in the second week of March. But at the same time, I will also look into the following, that it may be possible for us to get you access to the ebook version of this textbook. And if that's the case, I will then send out communication telling you such. Okay, so the purpose of this orientation lecture today is to essentially recap on content and material that you have already been exposed to. So I will not be teaching you anything new in this two-part video. All right, so we will be reviewing some of the algebra that you have already learned, and some of this content would have been taught to you from the time or the scope ranging from grade 8 all the way up to grade 12. So this is essentially some type of foundational work that we are now recapping on to ensure that when we meet in the second week of March, that you are adequately equipped to go through this mathematical journey with me. All right, so the content that we are covering today is essentially chapter 0 from the prescribed textbook, so this textbook here. All right, and the sections that I'm going to be covering with you is section 0.4 to 0.8 in this two-part video lecture. You will then be required to read section 0.1 and section 0.2. All right, so section 0.1 and 0.2 are essentially basically looking at real numbers and their properties. So I'm just going to make a note here that this is for you to self-study. So you just have to read it. This is work that you've already covered and is already apparent to you. And thereafter, section 0.3 is a section that I'm going to postpone. This is something that I will revisit and teach you once again at a later point. So starting off now, we're focusing on section 0.4 to 0.8. Right, so let's get on with operations with algebraic expressions. All right, so just coming out with this title, I mean, it must seem a bit complicated, but it really isn't. What we have to focus on here is what do we mean by algebraic expressions? Right, so you have obviously already worked with algebraic expressions, but now instead of hand waving here, let's actually provide a definition. All right. Right, so an algebraic expression is essentially a combination of mathematical terms and operations. Okay. And so what we are interested in here now is we want to be able to take an algebraic expression. So I'm going to give you an example of one that we would often be working with, but we would want to take an algebraic expression and then perform operations. So when we say operations, what are we exactly referring to? We're talking about the operations, the algebraic operations that you are already exposed to, and that is addition, subtraction, division, multiplication. So those are the prime suspects that we're working with. All right, so typical example of an algebraic expression would then be a polynomial, right? So let's be exact about this. So what is a polynomial? Right, so a polynomial which we often denote, and if you had to look at your textbook, it will be denoted P of X, right? So P of X. And this essentially, when you look at this, this now tells you that you're working with the variable X. So a polynomial in the variable X has the form P of X equals to, and here, so now just bear with me as I write down this expression. I will then explain to you what each of these terms are, right? Because I'm now going to be writing down mathematical terms, right? So we've got Cn being multiplied to a variable x raised to the power n plus, and now I'm indexing the c, right? So Cn minus 1, so it's dropped down, multiplied to x raised to the power n minus 1. And then we continuously add these terms where the sequence of terms are now decreasing in the index. So the next term would have been Cn minus 2 times x raised to the power n minus 2. All right, until we come to C subscript 1 times x raised to the power 1 plus C subscript 0 times x raised to the power 0. But what do we know about anything raised to the power 0? What do you get back, right? So x raised to the power 0 is essentially 1. Isn't that so? So I'll just make a note of that. So that equals 1. And therefore this term here is essentially just C0, because C0 times 1 is just going to give me C0. Okay, so let me move that. Not sure why it's not being erased at this point. Oh, it's gone. Okay, so I've just written down that Px has this form, right? But now let's be more explicit about this form. So what are these coefficients of the variables? What are the Cn, the Cn minus 1, the C1, the C0? Right, so in here, let's be specific. Right, so where C0, C1, all the way up to Cn are constants. So just numbers, right? So constants. And I want to specify that Cn must not equal to 0, right? So the leading term in here, that coefficient of x raised to the power n, and observe that n is the highest power in this expression, isn't that so? Right? Because n minus 1 is clearly less than n. And it has been decreasing in that fashion. So n is the highest power, and we're saying that the coefficient of the variable raised to the highest power must not be 0, okay? So why would we want to ideally say that? That's because, I mean, if Cn was 0, so let's just suppose, I mean, I had a 0 there, then 0 times x raised to the power n is 0. And that term in the expression becomes moot. So to ensure that it doesn't signify nothing, we are stipulating that Cn must not be 0, right? So that's important, right? More importantly, I also would like to specify that n is a non-negative integer. Okay, so what are the integers? The integers are the whole numbers, right? So we're talking about 1, 2, 3, 4, 5, and its negatives. But now I'm saying we are excluding the non-negatives, right? So we're not including -1, -2, -3, and so on. Okay. And so, yes, so these are the specifications about the coefficients and the powers of the variable x. And so whenever you have an expression taking on the following form, we then call this a polynomial in the variable x. But more importantly, I can specify one more thing. And so I'm going to add this in as a remark. Okay, I can say the following, that we call p of x just one moment. Okay, right. So just double checking that this was indeed on record. Right, so we call p of x a polynomial of degree n. So the highest power of the variable x is quite significant in here. All right. So if n in here was 7, then p of x would then be called a polynomial of degree 7. If n was 2, then p of x will then be called a polynomial of degree 2. Okay, and that's important for us to understand. So let's look at examples of polynomials. Right, so some examples. Okay, so one such example would be the following. 3x squared plus 7x minus 10. Observe that the only variable in here is indeed x. The highest power of the variable of the variable x is 2. Okay, there's 2. And observe that the rest of the powers are indeed decreasing. So that's 1. And here you can think of this as 10 times x raised to the power 0, isn't that so? And then, of course, each of these variables have a coefficient that's being multiplied to it. And observe, what is the condition from the definition here about a polynomial? We said that Cn, meaning the coefficient of the variable with the highest power, must not be 0. Here, our highest power is 2, and its coefficient is clearly non-zero. So this is a polynomial, right? So for now, I'm just being very, very pedantic, and I'm being specific about checking if the definition was satisfied. But of course, it might be extremely apparent to you without even having to check those steps that this is indeed a polynomial, all right? So it will become second nature. And so here, I'm just going to comment that this is a polynomial of degree 2. Degree 2. Okay, let's look at another example. Here we go. Right, I'm going to call this one P of y. All right, and P of y is equal to -7 times x raised to the power 10 r. Let me just undo this again. Right, so -7 times y raised to the power 10 plus 5 times y raised to the power 3 plus y. All right, so is this a polynomial? So now all of a sudden, I mean, in the definition, I was talking about a polynomial in x, but now I've written down something in terms of y. I mean, is that even allowed? Well, yes, so we're just replacing the variable x by the variable y, in which case, if this is a polynomial, then this is a polynomial in variable y. Okay, and what is the highest power of this polynomial? We observe that the highest power of the variable y is 10, and therefore this makes it a polynomial in variable y. and it is a polynomial consisting of degree 10. So that's important to take note of. Okay, and let's now consider another example. Right, so let's just say I said P of y equals to square root y plus y squared. Now, would this be a polynomial or not? Now, what's the issue that we're currently facing in here? The issue is that this has a square root sign in it, right? Remember, square roots are also sometimes referred to as radicals or surds. So if you come across this terminology, that's what I'm referring to. Right, so going back to the definition, what do we know must happen to the power of the variable? The power must be non-negative integers, isn't that so? And what is the power in here of y? So we know from what we've learned in school that the square root of y is the same as y raised to the power half. All right, so this term is now that term. So does this satisfy the definition of a polynomial, that the exponents must be non-negative integers? And clearly, it does not satisfy that because half is not an integer, all right? So when we're talking about integers, we're talking about the whole numbers, the positives and the negatives of them, all right? And here half is clearly not a whole number. So this is not a polynomial. And that's important. However, what we could say, this is still a mathematical expression, right? So I'll just remark. Right? P of y is a mathematical expression. Right? And we call this, so there's a general term, it's just called a multinomial, right? So called a multinomial. So very similar to, polynomial, right? So usually these words can be used interchangeably, but here we have an example of a multinomial which is not a polynomial. And so that's just something that you can keep in mind, all right? So just be able to pick the difference. However, so here, okay, let me just make a note, different color. All right, so here I've said P of y is a multinomial, but not a polynomial, but it's good to note that every polynomial is a multinomial. And therefore, sometimes we use the terms interchangeably. All right, so I'm going to repeat. Every polynomial is a multinomial, but here we've got an example where a multinomial is not a polynomial. So the opposite is not true. All right. So, I'm just stating this to share some facts with you, but of course, it may not be immediately necessary for you to apply such a thing in a question. All right, so now that we have an understanding about algebraic expressions, so I've just exposed you to two types of expressions. One was a multinomial and one was a polynomial. All right. So what we're interested in doing now is performing operations on these algebraic expressions. And as I mentioned at the start, the operations we're interested in is addition, subtraction, multiplication, and division. All right, so we're starting off with subtraction. And the reason for that is because when we're dealing with subtracting expressions, you are, in a sense, also using addition. So we're gonna see that, all right? So how do we go about subtracting two algebraic expressions? Right, so the idea here is that we will group like terms and then perform the operations as you usually would. Right, so when you're performing the operations, you're essentially going to perform the operations on the coefficients of the variables, okay? So the numbers in front of the variable, that's what you will be performing the operations on. Okay. So I'll make a note here. We focus on the coefficients of the variables. All right. So the question here is to simplify the following expression. So this expression says 3x squared times y minus 2x plus 1. And then we have to subtract the next expression from it, which is 4x squared y plus 6x minus 3. All right, so observe in this expression, we have more than one variable. We've got x and we've got y. All right, and so note this is indeed a multinomial, right? It's a multinomial of more than one variable, and the variables are x and y, just to make it apparent. So I'm just using these words and jargon, I'm throwing it around, and these are mathematical terms that you will eventually get used to, okay? So there's no need to stress if suddenly these things seem foreign, all right? So remember, we're just recapping on stuff that you've done in school. The difference is now that the stuff that you've done in school is being presented to you on a different level, all right? But you have definitely seen expressions of this form before, right? You've definitely seen 3x squared plus 7x minus 10, etc. Okay. Right, so we're interested in subtracting. So how would you go about doing this? Right, so firstly, what I'm going to do is I'm going to rewrite the terms by removing the brackets. So I've got 3x squared times y minus 2x plus 1. And now what I want to do is I want to distribute my negative into the second bracket. So if I'm going to do that, I've got negative 4x squared times y, and I've got negative 6x. And then finally, when I distribute the negative to the last term, this negative times the negative gives me a positive, and therefore I get positive 3. All right, and so now that this has happened, the next step for us to do is to group the like terms. So what am I talking about? What is this grouping of like terms? Right, so when we're grouping like terms, we are looking for the terms that have the same variables. So this first term in particular has the variables x squared times y, right? So I'm going to underline that. Is there any other term in this expression that also has x squared times y? And observe yes, right? So this is 1, 2, 3, 4. So the fourth term has exactly the same thing. So that's what I mean when we say we're going to group it, okay? Right? Then is there anything else that I could possibly group together? Let's take a look. Right, so then here I've got x, and similarly here I've got x again. So these two candidates, I'm now going to double underline them in green, are grouped. And then what's left over? The things that have not yet been underlined are constants. Right, so I've got a plus 1 and I've got a plus 3. So I've sort of got my 3 groupings sorted out in my head. And now that I've got these groupings arranged, the next thing to do is to perform the operations. All right, so we want to perform the operations. And how do we perform the operations? We focus on the coefficients of the variables, and we just follow through. So if there's a minus sign, then you would subtract. If there's a plus sign, then you're going to add. So that is why I said in subtracting the algebraic expression, there'll be a combination of addition and subtraction. All right, so let's work with the underlined purples. All right, so we've got x squared y, so 3x squared y minus 4x squared y. So when I perform the operation on the coefficients, I've got positive 3 and minus 4. What is positive 3 minus 4? It's negative 1, all right? So that means I'm left with negative 1, or I could just say I'm left with negative x squared times y. And so I've performed the expression, I've performed the operation on those like terms. Let's go to the next set of like terms that we had. That is minus 2x and minus 6x. So working with the coefficients -2 and -6, we know that -2 minus 6 is just going to give me -8. So that means I've got -8x. And then finally, the last group terms are the constants, +1 plus 3. +1 plus 3 gives me +4. And so that's it. So this was the simplification of these two algebraic expressions. The key thing here was to distribute the negative into the second expression, and then we grouped like terms and we performed the operations. All right, so that was subtraction. We're now going to talk about multiplication, so products. All right, so again, you've already been exposed to these types of products. I'm just going to be refreshing your memory on them. Okay, so let's look at part 1. So in here, we've got x being multiplied into a bracket. And this bracket has y plus x. So how did you go about multiplying these things previously? All right, so all you did was you distributed the x into each of those terms, isn't that so? And so that's precisely what you do here. So I'm just summarizing and recapping on the multiplication rules we learned before. All right, so this was the rule of distribution, and therefore it's equal to x times y plus x times z. So I'll remark this is distribution. Okay, rule 2 and rule 3 actually have something in common. And so these things here, again, we're distributing, but if you recall the rule you were taught in school, you were taught FOIL. First out is in is last, right? And so if we had to write down what this is equal to, this is equals to x squared. When you then multiply the other terms, you've got bx plus ab. So I'm just going to group them and write it as a plus b times x. And then finally, a times b. So that's plus ab. Right, and then similarly for part 3 in here. So we've got ab times x squared. Right, so I've multiplied those two. Then you can multiply ax to d. Okay, and then you can multiply c to bx. All right, and then in there again, just like how I grouped these things together, you would observe that you can group AD plus BC times X. And then finally, the other outers, we've got C times D. Okay. All right, let's go to point 4 and 5. Again, point 4 and 5 are similar. All right. So these here, as you can see, is just the squaring of a binomial. Okay, and you've learned a rule for this. How do you square a binomial? Right? So remember, you square the first term, you square the last term. So that becomes the first term, x squared, square the last term, a squared, and then you multiply the two and you double it. So that becomes plus 2 times ax. All right. And then if we had to repeat where the sign is now different, same procedure, square the first term, square the last term, multiply the 2 and double, but now we've got negative 2ax. All right, and looking at point 6. So here we've got the product of these two brackets. And what's the difference between the two? One has a positive and the other has a negative, but the terms are exactly the same. Isn't that so? Right? So in here, if you had to just quickly recall, what rule was this? This is the product of sum and difference. Isn't that so? Right, so I'll just make a note. Product of sum and difference. Right, and what did you do when you had the product of sum and difference? So like terms, but different signs. All you did was you squared the first term, right? You squared the last term because, I mean, the terms are exactly the same, right? And because the signs are different, you put a negative in the middle. And so that was that. And then, of course, just to add 7 and 8, here we're dealing with our trinomial. So you could, in essence, split up this, right? And you could say that you could write this down as x plus a squared times x plus a. And then you multiply these two together just like how you would have multiplied in step 2 and 3 using FOIL, right? You'd be using the rule twice. Okay, and when you do that, you then arrive at the following simplified answer. X cubed plus 3ax squared plus 3a squared x plus a cubed. All right. So all of the signs are positive when the sign used in here is also positive. So now what happens when we're using a negative? Right, so in here, you then have x cubed minus 3ax squared plus 3a squared x minus a cubed. Okay, so all of the terms are exactly the same in these answers, but this negative in here has a significant impact on the signs when you have to multiply out. Right, so this is just a summary of the multiplication rules that you have been exposed to before. All right, so of course, I mean, looking at these things where they're written very generally in terms of just variables and constants, meaning we've got letters A, B, and C, and D, etc., does look sort of out of reach. But of course, when you're working with physical numbers and you're doing actual examples, then these things return to you. Right, so let's look at examples. Okay. Right, so we've got x minus 4 all squared. So this is squaring a binomial. Right, so how do we square a binomial? What do? We square the first term, we square the last term, and let's do that. So we've got x squared, the last term is -4, so you square it, you get positive 16. And then you multiply the two terms and you double it. Right, so when we multiply, we now have a negative, so you have to incorporate that. So that's -2 times 4x, and -2 times 4x is -8x. And so that's what I've got in here. Let's look at the next example. We have the product of two expressions, but now let's look closely at these expressions. Observe that the first one, if you observe by looking at both of them, that they have exactly the same terms, don't they? So the first term is the root of y squared plus 1. And again, we've got the root of y squared plus 1. The second term is 3. And again, we've got a 3. The difference between the two are the signs, isn't that so? So we've got a positive in here and we've got a negative in here. And then based on the rules that we've just gone through, this is just the product of sum and difference. And so what do we do when we're in that situation? Product of sum and difference, you just square the first term, you square the last term, and you put in negative. So let's do that. Okay. Right, so we're going to square our first term, which is the square root of y squared plus 1. And then we're going to square the last term, which is 3. So that's 3 squared. And then we put a negative in between. And now we simplify. So what happens when you square a square root? You actually undo what has happened. And so what's left over is the expression inside the square root. So we're left over with y squared plus 1. Okay? And then we're subtracting 3 squared, and that's just 9. So let's simplify. What is our answer? It's y squared plus 1 minus 9, and plus 1 minus 9 is just minus 8. And so that is just a quick refresher, 2 quick examples that makes use or gives you an application of these special products that we are familiar with. All right. So we've looked at addition, subtraction, multiplication, and so now we're going to talk about division. Right, so dividing a multinomial, so I've already exposed you to this term multinomial, isn't that so? So I said it can be used interchangeably with polynomial, okay? But then I gave you an example where we had an expression that was a multinomial, but not a polynomial. So you have to be careful about it. But I mentioned that every polynomial is a multinomial. Right, and then we say dividing a multinomial, so we have an idea of what that is, by a monomial. So what is a monomial? Right, so a monomial, so I'm just ensuring that I expose you to the different terms. These terms are mentioned and defined in your textbook in chapter 0, so please ensure that you also recap on them. Right, so a monomial is basically an expression that only has one mathematical term, mono for one, right? So one mathematical term. And that's it. So an example of one mathematical term is just x. I mean, that's it. It's one thing. Or maybe 3 times y. So 3y, it's just one term, okay? So if I had to quickly go back to these examples, x squared minus 8x plus 16, each of these things in here are monomials. So x squared is a monomial, 8x is a monomial, and 16 is a monomial. So the sum and difference of this monomials gave us a polynomial. So by combining monomials, so one term, you get the many, right? You get the poly. So mono for one, poly for many. So I hope you've seen the connection between the English and the mathematical definition. So I'm just trying to extrapolate the relationship there for you. Right, so polynomial, many mathematical terms, monomial, one mathematical term. And so multinomial is essentially explaining the same thing, multi, more than one, right? So how do we go about dividing? So the trick here, if you have a multinomial or a polynomial being divided by one term, is to then do the following. So you will then divide each term in the polynomial by the denominator. Right, so what is a denominator? It's the bottom expression of the fraction, right? So whatever you are dividing by, right? And then also preserve the operations. Okay, so I mean, these are a lot of words. So let's actually put this into practice and see, what am I actually talking about? All right, so here's an example. 4z cubed minus 8z squared plus 3z minus 6. Right, so clearly so this is a fraction clearly, right? So you've got an expression divided by another expression, right? Whatever's on the top, if you had to recall from what you learned in school, is called a numerator of the fraction. And whatever's on the bottom is the denominator. So these are the terms that I'm using. Right, so numerator divided by denominator. And observe that the numerator is a polynomial, right? So it's a polynomial in z of degree 3, right? The highest power of z is 3. So that's a polynomial. And we are dividing by a monomial. It's a single term, right? So just to make a note. So we've got a polynomial being divided by a monomial. And that's precisely what we want to discuss. Right, so the trick that I just mentioned above is you divide each term in the polynomial by the, why did I write it like that? By the denominator. Okay. Right, by the single term in the denominator. And our single term in our denominator is 2z. So every term in here in the polynomial gets divided by 2z, and we preserve the operation. So let's look at how we're going to do that. So when I say each term gets divided, I mean take the first term, which is 4z cubed, and then divide it by 2z. That's it. But then respect the operation, so there's a minus, so keep the minus there. Then take the second term, which is 8z squared, and then divide it by 2z. Again, respect the operation, so there's a plus. Then I'm going to take the next term, which is 3z, and I'm going to divide it by the monomial in the denominator, which is 2z, and then do the same for the last one. So that's 6 divided by 2z. And so then once you're done, start simplifying. So what's actually happening here? 4z cubed divided by 2z. So I mean, those are going to cancel. And 4 divided by 2 is 2. So I'm now left with 2z squared. Look at the next one. Right, so again, I've got a cancellation occurring. 8 divided by 2 is 4, and I'm left with 4z. Right? These cancel, and I'm left with 3 over 2. So you can leave it as 3 over 2, or you can write 3 over 2 as 1.5, right? So however you prefer. And then here, 6 divided by 2 is 3, and it's still being divided by z, so I'm going to leave that unchanged. And so this is what we mean when we say take your multinomial or your polynomial divided by a single term from the denominator. All you do is ensure that each of the terms in here get divided by that 2z. Okay, right, so that's division. All right, and then since we spoke so much about multiplication, now what about the opposite? So what about factoring? Right, so here is a list of common things that you've already been exposed to. Again, it just looks foreign because, you've got it in general form. You've got variables and you've got constants, A, B, C, D. But if I put numbers to this, you'll be like, oh yes, I've done this, right? So you've technically done all of this, right? So don't feel afraid by looking at this and thinking, but no, I haven't. You actually have, right? And we're going to see that in a moment. Okay, so, right, so what's happening here when you've got, so in expression 1, x times y plus x times z. So in order to factorize this, you essentially need to pull out the common factor. And what's the common term in here? The common term in here clearly is x. So that's what's happened. So we've pulled out the x, and that's what's written here. And then whatever's left over is what's written in the bracket. So that's y plus z, okay? And then just looking at the next few points, I can actually group them together for you. So point 2 all the way up to point 5 is essentially dealing with the same type of factorization. Right, so you've dealt with factorization of a binomial before. And remember, when the coefficient of the x squared was 1, you then looked at how could you factor the constant, right? And once you've got out the factors, you looked at whether you could express the coefficient of x as the sum of those factors. So this is something you've been exposed to before, and point 3 to 5 is actually dealing with the same type, right? And then finally, 6 and 7 is just dealing with, let's see, not 6 and 7, let me undo that. Right, so 6 is dealing with the difference of 2 squares. So we've already seen this form before, all right, when we discussed the multiplication. And then 7 and 8 are dealing with cubes, all right? So the sum and difference of 2 cubes. All right, so I'm not going to spend too much time on this because it can be daunting to look at this, but it is something that you've already been exposed to, and it's going to be much more easier when you look at it in defined examples. All right, so let's look at that. So factorize the following. All right, so we've been given a long expression. 8 times a raised to the power 5 times x squared times y cubed, and then we've got minus, and here's the next term, 6a squared b cubed y times z, and then the third term, 2 times a to the power 4 times b to the power 4 times x y squared z squared. All right, so how should I even approach such a problem, right? Because it's clearly a long list of variables in here. So the first thing for you to do is to just take a moment to observe what has been written in the question, right? And try and find commonalities. Are there any repetitions? Are there common things in each of these terms? Right, so what's common in here? So firstly, each of these terms has a's, right? So there's a variable a. Is x common to each of the 3 terms? No, it's not, because it's missing from the second one. So let's look, is y common to each of the 3 terms? Yes, y is, right? So I'm going to double underline the y's. So that means that when you're factorizing, these are the suspects that you could now pull out a common factor of, right? So the idea is you will now pull out the highest common factor. So what is the highest common thing that I could pull out amongst them? So firstly, before we pull out the variables, is there a constant that I could possibly pull out? So 2 is certainly a commonality between these coefficients. So I'm going to pull out 2, right? Because I can factor out a 2 from the 8 and similarly from the negative 6, right? Then I've underlined all the a's. So what's the highest common factor that I could pull out? Observe that a squared is what I could pull out. So I'm going to write down a squared. And then I've underlined the y's. So what's the highest common factor that I could pull out here? And observe that the highest thing that I could pull out is just y. Right, so now that I know what my common factor is, what's left over? All right, so in the first term, if I pull out 2a squared y, I'm left over with 4, right? I've pulled out a squared, so that means I've got a cubed left over. The x squared is unchanged. I've pulled out y, so I'm left with y squared. Okay, and now let's work with our second term. We've got a negative in there. I factored out 2, so I'm now left with 3, right? Because 3 times 2 gives me 6. Pulled out a squared, so there's no more a's left over. B cubed is unchanged. I pulled out y, so there's no more y's left over, and z remains unchanged. And now just focusing on our last term. All right, so we've pulled out 2, so there's the constant left over is just -1. I pulled out a squared, so I'm now left over with a squared. B to the power 4 is unchanged, x unchanged, y, so I pulled out y, and therefore I'm left over with y, and z squared is unchanged. And so that is how we pull out the common factor. A good way to check if you've done this correctly is to just distribute this back into each of those terms and make sure that you've got the original expression. Okay, next. Factorize x squared plus 8x plus 16. All right, and so now this is using the rules that I put in curly brackets 2 to 5. All right, so how do we go about doing that? So the trick is to look at the constant term and find out what are the factors in here. So the factors that we could possibly work with is 1 and 16. We've got 4 and 4. Is there anything else? 2 and 8. And that's about it. So we've got these 3 sets of factors, and we need to check which combination of them could give me back positive 8. So from the list that I just mentioned, we would all agree that 4 and 4 would give me back 8. And so therefore, the answer here is then going to be, so we've got 2 brackets, right? And we've agreed that it's going to be 4 and 4. I need positive 8. And when I multiply these 2 values together, I must get back positive 16. So clearly the signs that work is going to be x plus 4 and x plus 4. So positive, positive. All right. And just to check, positive 4 times positive 4 gives me back positive 16. And when I add these 2 values together, I get positive 8. And so observe that these 2 terms are identical. So I could just write this as x plus 4 squared. Okay, so that's important. All right, third example, x cubed, sorry, x to the power 6 minus y to the power 6. All right, so we've got 2 expressions on each side and a negative in the middle. Right, so I might feel a hunch that perhaps the rule I'm looking for is the difference between 2 squares, right? But I mean, the difference between 2 squares requires that the terms be expressed as squares, but I don't have that. What do I have? I have the terms raised to the power 6. But is there a way for me to manipulate this such that I can express them as 2 squares? And yes, I can. All right, so observe that x to the power 6 can be expressed as x cubed squared. And y to the power 6 similarly can be expressed as y cubed squared. So remember, we multiply those powers. So 3 times 2 gives me 6, right? So of course, these 2 expressions are identical. All right, and so now this takes on the form of the difference between 2 squares. And so what do we do? How do we write down those factors? How do we factorize? We simply take the one term and write it as, with a positive sign, and then the second bracket with a negative sign. So that means the 2 factors that I now get out here is going to be x cubed plus y cubed. Okay. And the next one will be x cubed minus y cubed. And can this be factorized further, or can I stop here? Well, let's go back and look at our rules. Don't we have further rules to factorize the sum of two cubes and the difference of two cubes? Yes, we do. So then you could then work with this expression and factorize it further, and similarly work with this expression and factorize it further, okay, using just the rules that were stated above here. Okay, so that is our factorization. Right, and then lastly, before we end part one, we're just going to quickly talk about fractions. I mean, we've already spoken about fractions when we dealt with a multinomial divided by a polynomial. So, I mean, we've seen that a fraction has an expression divided by another expression. So this is your numerator, that's your denominator. But of course, when we're dividing, it's important to note that the denominator should not be zero. If you're dividing by zero, you're going to end up with something that is undefined. All right, so the main thing here is, how do we simplify fractions? All right, so that's what we want to do. So this first step is to factorize, and that's why we just went through that procedure. So we want to factorize and cancel like terms. And the next thing to do is, if the step fails, right? So if you can't factorize and cancel, so if one fails, then we will rationalize the denominator. And this typically happens when you have radicals in your expression. So I mean roots. Okay, so let's look at these examples. Right, so I've got x squared minus x minus 6 divided by x squared minus 7x plus 12. Right, so the difference between what we did before and the division that we're doing now is that before the denominator had a single term, but here now the denominator has a polynomial, okay? Right, so we need to factorize the top and factorize the bottom. So if I'm going to factorize the top, all right, so factors of 6 such that when added together gives me -1, the coefficient of x, what would work? I'm going to work with 3 and 2, and therefore I think that -3 and +2 will work. Let's check. So -3 plus 2 is indeed -1, and if I had to multiply them together, -3 plus 2 gives me -6. Let's factorize the denominator. Right, factors of 12, that would work. The factors that would work are 3 and 4, right? And I need -7. So I'm going to take x minus 4 and x minus 3, right? So -4 minus 3 gives me -7. And then, of course, when I multiply the two, -4 times -3 give me +12. So these definitely work, right? And let's just see. Here, the other thing to note is that in this question, we should specify that x minus 3 should not be 0, right? Because observe, we are now canceling these terms in here. And now what are we left over with? X plus 2 divided by x minus 4, okay? And so we require in here again that the denominator must not be 0. So we could specify in here that x should not be 3, nor should x be 4, right? So I needed to ensure that I'm not canceling out zeros in here. That wouldn't make sense. Right, next question. Now I've got some radicals floating around in my fractions, don't I? Right, so this might indicate that we're going to be rationalizing the denominator. So I do know that rationalizing the denominator was indeed taught in school. So if you've forgotten, that's okay, because we're recapping on it. Right, so in here, I mean, is there any way for me to cancel out things and get a simplified version so it doesn't seem apparent? So how do you rationalize the denominator? Let me make a note. Right, so the idea in here, when you rationalize, is that we multiply by 1. So because when you multiply anything by 1, you aren't changing the expression, right? So how do you multiply by 1? When I say multiply by 1, I'm just saying make sure that whatever you multiply by, you divide by, because clearly x divided by x, provided that's not 0, is going to give you 1. So whatever you multiply by, you make sure you divide by that same thing so that you're getting 1, all right? And so what should this x be? What should it be chosen to be, right? So we will multiply by the conjugate of the denominator. Okay, so what, spelling, denominator. Right, so the conjugate of the denominator. So where's our denominator? There it is here. Square root 2 minus 1. And what is its conjugate? So if you've forgotten what we mean when we say conjugate, right? So if we have a plus b, then its conjugate is a minus b. So the conjugate of an expression is obtained by simply changing the sign in the middle of the two terms. So if this was a minus b, then the conjugate becomes a plus b. So just change the sign. All right. So what did we say we're going to do? We're going to multiply by the conjugate of the denominator and then divide by the same thing. So I should make a note. Right? And divide by it. All right, so what's the conjugate of square root 2 minus 1? It's going to be square root 2 plus 1. So we change the sign, right? So I said the idea is that we multiply by 1, all right? And so what should this 1 be? We've just explained that it's going to be the conjugate divided by the conjugate. Right, so this 1, we're now being specific, okay, is the conjugate of the denominator. So we multiply by it, it's square root 2 plus 1, and we divide by it, square root 2 plus 1. Square root 2 plus 1 divided by square root 2 plus 1 is 1, right? Anything divided by itself is 1. And so we're preserving the idea and we're actually keeping to the fact that we're multiplying by 1. Okay, and so now all we have to do is multiply what's happening in here. So let's multiply the top. So we're going to use FOIL, okay? So square root 2 times square root 2. So when you multiply by the same thing under the square root, it undoes the square root. So we're left with 2. Then I've got square root 2 times 1. Then I've got 3 times square root 2. And then I've got 3 times 1. So that's the multiplication happening at the top. Let's work with the bottom. Now observe very carefully what's happened at the bottom. Isn't this the product of sum and difference, right? Because we're taking something and we're multiplying by its conjugate. So what do you do when you do that? Based on the rules we've learned, you square the first term. So square root 2 squared is just 2. You square the last term, so that's just 1. And you put in a negative sign. And that's it done. And so all we have to do now is just simplify. All right, so 2 minus 1, I mean, that's just going to give me back 1. So we're dividing whatever's on the top by 1. Okay, and so therefore, we're just left with 2 plus 3 in here. So that's 5. And then root 2 plus 3 root 2. That's 4 root 2. And that's it, divided by 1. So it's that unchanged. Okay, and so just before we end, addition and subtraction. So addition and subtraction of fractions. So I'm not going to be covering anything in here. Just to remind you that this is something that you've done before, so I want you to recap on your own. And I want you to be able to do the following. So if you had a fraction a over b being added to c over d, please ensure that you're able to do it. And similarly, if you had a over b minus c over d, ensure that you do it. How did you go about doing it? You had to find the common denominator. And just for me to specify b and d is not 0. I mean, we can't divide by 0. Right, so go and recap about how to find the common denominator and add and subtract. Yes, so this brings us to the end of part 1. So that's it from me, and I will see you in part 2 shortly.